Hi, let's talk about angular momentum of a point particle. Angular momentum is the natural generalization of linear momentum to angular motion of a point particle. Consider a point particle moving in space. Consider an origin of coordinates and a coordinate system. We define angular momentum of the point particle as the cross product of the position vector r and the linear momentum p. Because of the properties of cross product, the angular momentum is a vector that is perpendicular to both r and p. If the overall motion of the particle is counterclockwise, the angular momentum will point up. If the overall momentum of the particle is clockwise, the angular momentum will point down. If you are familiar with the right-hand rule, you can apply it here. If you point your fingers of your right hand in the direction of r and curl them in the direction of p, your thumb will point in the direction of angular momentum. Just as the linear momentum, this is a very useful magnitude. It quantifies the angular motion of an object as with respect to a certain point. Look that, depending on the origin of coordinates you choose, the angular momentum can be different. Just as with linear momentum, we can calculate the total angular momentum of a system by adding the angular momentum of each element in the system. When we introduced linear momentum, we saw that the derivative of linear momentum with respect to time is equal to the force, and we could rewrite Newton's second law in terms of that derivative. Let's do something similar here. Let's calculate the derivative of the angular momentum with respect to time. That is the derivative of r cross product p. This is the derivative of a product, therefore it is the derivative of the first term times the second term plus the first term times the derivative of the second term. The derivative of r with respect to time is the velocity v of the particle, and the derivative of p with respect to time is the net force F. Now the first term is v cross product p, and the second term is r cross product F. Well, vector v and vector p are parallel. They only differ in the mass multiplying p. Because the cross product of two vectors that are parallel is 0, this first term goes away. So we have that the derivative of the angular momentum with respect to time is r cross product F. But this happens to be the torque. So we have that the rate of change of the angular momentum of a system is equal to the torque applied to it. If there is a net torque, there will be a change in angular momentum. This is the extension to rotational motion of Newton's second law that says that if there is a net force, there is a change in linear momentum. So no net force, no change in linear momentum, no net torque, no change in angular momentum. This leads to two powerful conservation laws. In the absence of external forces, the linear momentum of a physical system is conserved. In the absence of external torque, the angular momentum is conserved. If you have a multi-particle system, there might be internal changes of momentum and/or angular momentum of the particles, but the total momentum and angular momentum of the system will be conserved. Think about the Earth in its motion about the Sun. You might know by now that its trajectory is not a circle but an ellipse. This means that in January we are closer to the Sun, and in July we are farther from the Sun. The Earth moves on a plane, the plane of the ellipse. If you look at the equation of angular momentum, you see that L is equal to r times p. Consider the origin of coordinates at the Sun. R is the vector that goes from the Sun to the Earth, and p is the vector tangent to the trajectory. Therefore, L is a vector perpendicular to the plane of the trajectory. But L is proportional to r times m times v. When we are closer to the Sun, r is smaller, which implies that v needs to be larger. So in January we move faster with respect to the Sun, and in July we move slower. Now think of when you ride a bike. The wheels of your bike have an angular momentum that is pointing to your left. If you tilt a little bit your bike, what you are adding an angular momentum in the horizontal direction. Use the right hand rule to think this through. Well, because you and the bike are the same system, the total angular momentum needs to be conserved. If you are adding some angular momentum in one direction, the bike U system will compensate to keep it constant. That is why you don't actually fall. Well, I'll let you that for you to think. May science be with you.